Okay, so here is uh, chapter 3, basically the third part of our introduction to the relational database model. As I said, this is really meant to be more of a complement to the to what we had done, what we already had posted in terms of those recordings. So it's not, some of the stuff similar. I mean, so we'll cover this, cover the same things. I just wanted to add some additional. I wanted to put this out there so we have a little bit of, if there was any confusion coming off of the first deck, to get a little bit more clarity. Okay. So this is number 3. We're going to talk more about the relational database model. Okay. We're going to talk about the database, the relational database model. We talked about it in chapter 2. We're going to talk about more in depth because this is really the focus area for what we're going to be talking about. The basic component, which is, as we said, relations, i.e. tables. And then relations are logical constructs composed of rows, which mathematically speaking we call them tuples, and then columns, rows and columns, which we refer to them as attributes. Right? And all of these are implemented as table in a relational database. So also talk a little bit more in detail about the data dictionary, the system catalog, how we deal with things like redundancy and indexing. Okay, so to start off with here, this idea of a logical view of data. Remember we talked about this idea of data modeling. So what we're doing is we go out and we look at a particular business operation. Right? So we get a description of it, define what the business rules are, and then translate that into a logical model or a model. So the idea is we use the logical model in the relationship, the representation of the data and all of the relationships. Remember, the whole thing about relational databases are we have multiple tables that are related through common fields. And so what we do is this idea of is, if you do the design the right way, if you create a logical view correctly, you have a simple and effective design methodology. And then the idea of facilitated by the creation of data relationships based upon logical construct called a relation or table. Some characteristics of a table, some the different characteristics of it. Two-dimensional structure, rows and columns. Each row it refers to a single entity. So think about a sales order. Think about you buy something at Amazon. You buy one. That as a one that reflects one event. So you would have one entry in a table if you're buying something. Each column represents or field represents an attribute. Each column has a distinct name that usually, if you do it the right way, should reflect what the function is. All values in the column must have the same data format. So what happens is if you define a field as having a date in it, you have to have a date in it. And what happens is the databases, these DBMSs are smart enough to be able to look at what you're trying to put into the field and will stop you if you are trying to put something. If you try to put letters into a date field, it will stop you. Order of the fields, order of the rows and the columns are immaterial. It really in a table. So what will happen is it will enable you. So the thing we had talked about with file systems around this dependency of structure or where things are at. So basically we've broken that, or we've eliminated that. And then last and not least, but it's also an important thing to remember, is every table has to be unique, or has to have a field or a combination of fields that will uniquely identify the row. So every column or every row has to have at least one column that makes it unique. And that's called the key. So what will happen is, and usually what a lot of times organizations, so maybe there's a field that is unique, But a lot of times what we'll do is we'll fake it. All right, so we'll create a field and we'll just simply put a number in it, you know, 0 to infinity. All right, so the first row will have the first row in the table will have a 0. Second row have a 1, 2, 3, so on and so forth. So it becomes a the terminology we use that as a surrogate key, but it's, you know, it works. It basically gives us the ability to assign a unique, ensure that every row in that table, um, every row in that table is unique. So we talked about keys. So once again, the thing that makes the things that that makes that table unique, the row in that table unique, is a key. And a key can be more than one field. Could be one field. Could be more than one field. So it ensures that each row in the table is uniquely identifiable and establishes a relationship amongst tables. That's kind of what a key is used for. The primary key is the attribute or attributes, combination of attributes that makes it unique. That's called the primary key. So every row has got every table has a primary key in it. And every row that's in that table has a unique value. So, you know, as we talked about the determination here, you know, basis of establishing the role of a key based on the relationships between the attributes. So the idea is that, you know, we use these keys as the means by which we tie these tables together, link these tables together. So we'll talk about dependencies, you know, functional dependence, you know, entire of attributes. So some of the stuff, once again, this goes back to the mathematical basis of this idea of functional dependence versus full functional dependence. You know, the collection, you know, determined is necessary for the relationship. This is all that. That's some of the terminology that gets associated. Just some of the stuff you want to know about just the keys. So the idea of a composite key. If you have more than one field that makes up a key, it's called a composite key, and then each key will have its own attribute. All right. Now this part right here, so we started about the integrity. All right. If every row in the table has its own unique value, its own unique key, then it will have entity integrity. All right. All values in the key must be unique, and no key attribute can contain a null. All right. The reason for this, the mathematics of it. All right. So this is, you know, basically in order to fulfill the mathematical, you know, basis for this, you know, we have to make sure that every row has a unique key. So this is just some of the terminology we use around it. Different types of keys. All right. So, you know, entity integrity is one thing we look at. Null is just simply the absence of a value. The other term we say referential integrity. All right. Basically, what it means is the connection between two tables. All right. We make sure if there's a connection between two tables that the values are accurate between those two. That there's a correct connection between those two. So if there's a row, that if we have a relationship between two tables and there's a row, there's a field that doesn't align, doesn't have a value, a correct value, that matches back, the database is considered broken. All right, because you'll never be able to get that. You'll never be able to find that record again when you did a query. So that's in real life, that's something we're always looking at. You know, if you break, the terminology is when we break referential integrity. You know, that usually people start running around and making sounds. So, all right, so this is just a simple relational database. Two tables. All right. Linking. This is the vendor product. All right, so this is the vendor code. These are all the products. And then this is the vendor, and it matches on the vendor code. So if we look at one table, if we look at this here, we can go through and we can link. Basically, what this allows us to do is actually connect two tables together. So what we get is we get all of the data, that is in both of these tables. We can access both of those, all the data across both those tables, because they are linked together by the vendor code. So this is just some of the more terminology. The ones we really want to know: the primary key and the foreign key. The terminology we use is on the vendor code here. This becomes of the foreign key. All right, so the relationship here is one vendor can sell multiple products, one or many products. All right, so what happens is in this table here, we will call this field a foreign key. Right, so it's just some terminology. Some of the different types of integrity rules, so I'm not going to go into massive detail on this. We talked about the entity integrity, which means every row has a unique value in it. Referential integrity means the two tables, the keys between the foreign key and the primary key match up, that things match up correctly. Just an example of the different integrity rules. Let me talk about nulls. So nulls are, basically used to. A null is not a blank. It's not a zero. It's a null. It doesn't exist. So if you put null values into a field in a database, it will, you can check to see if it is null. Nothing's ever been put in there. All right. So some ways to be able to deal with this is you can actually put a rule that says the field cannot be null. You got to put something into it. Or in addition, you could also put a rule that says, when we say these constraints, a rule that says that table has to be, that field has to be unique. Right? So a couple different ways we can deal with this, defining the rules. This is, we said, relational algebra is the basically the theoretical basis of all this stuff. It was, Dr. Codd built his theory off of relational algebra. So the idea is that so long as we play by his rules, the results we get back are correct. So this set right here, this information right here, is actually derived from relational algebra. So select, project, union, and intersect are the functions that we use in relational algebra. All right. So it's all based upon, relational algebra is based upon set theory. So the idea is you have two sets, and what you'll have is information that's in one table, or you have all the information across both tables, that's the union. Information that's in both tables, together, that's the intersection. I've seen that before. And then the select is how we get the data, basically a horizontal subset of a table. All right. So this is this is an example of a selection. One of the things that's interesting about this is that the term we use in the SQL to pull data out is a select command. All right. So basically, that's the reason it's select, is because that's what we do on the mathematical side. And this is examples of the relational algebra. So difference, products. This is all the basic. This is the relational set operations. So this is all of the things that we can do within relational algebra that actually translate to what we do in a relational database. So we have a concept here called a join. All right, allows information to be connected from two or more tables. So this link. So we'll go back here for a sec. Just take a look at this. right here, when we link these two tables together, the term we use is we join these two tables together. So we don't say use the word link, we use the word join. So you can join two tables together using a common field. All right, so we can do a, like say, a natural join. So it's all so we link the tables by only picking the rows with common values. All right. Or we have a couple different ways that we can do what gets termed here as an equijoin. So it matches specific conditions, specified columns of each table, or they call it theta join. All right. But most part we use like a natural join, or excuse me, inner join, outer join. So there's a couple different ways these joins get done, like left outer join, right outer join. So the idea of a outer join is match pairs are returned. What I'll do is it will match everything up, and then anything that's unmatched in the other table are left null. So this is really good when you're trying to match things up and see if there's things missing in a table. What you do is you can take two tables, you do a left or a right outer join. And basically what the left and right outer join means, what table, the left-hand table or the right-hand table is the one that has the that will have the matching value in it. And then just some examples of joins. So the data dictionary. So the data dictionary, is really a tool in the DBMS which enables us to track everything. Right? So it describes all the tables. It uses a catalog, all the different tables, what they are, what the fields are, what the relationships are all maintained within the data dictionary. We're talking about the relationships within the database themselves. I think we had mentioned this before, one-to-many relationships, which is most the norm, as we say, the norm for relational database. One-to-one, one entity can be related to any others. And then this idea of a many-to-many, composite join, or excuse me, Cartesian product, which is where we take all the fields and we match all combinations of all fields together. So this is an example of a one-to-one relationship. One professor is in one department. So just different examples of this. So the way the magic or the secret of this, within databases, we can control the type of data redundancy through use of foreign keys. All right. So the idea is, if we do this, if we design the database the right way, we can ensure that we're not going to get redundant data. That's what's actually kind of where people will complain is, well, it takes a lot of work to build up a database. Well, yeah, because you have to set it up the right way to get the right answers out of it. All right. So the idea is, by using a foreign key approach to move data, to store data, you can actually eliminate, and this actually, we go through a series of steps when we're designing a database, different forms, and this is where that all gets designed out as we go through. So this is once again, another example of a diagram relational databases, 4 tables. And as you'll see, actually this is a little better example. We have this, 1 on the one side, infinity on the other. All right. The infinity sign means it's the many. So we have a one-to-many relationship, one-to-many relationship, one-to-many relationships. Same field, linking together. As you can see in this field, or in this table right here, we have a composite key. 2 keys. 2 fields that make up a key. It makes it unique. And then the other one's the invoice number, customer code. So the idea of an index, so there's actually what a database will do, has done, is it will read everything. How it does this, it will read all of the data in the database and match these things up. So if you can imagine, if you get a million rows, a couple million rows in a database, it can take a while to do this. So with DBMS, a function of the database management system, one of the things they do to kind of speed things up is create what we call an index. So what it is it's sort of an enables us to a shortcut way of being able to look up data. Right? So it's actually another table. It's actually an index is technically it's another table that gets associated with the table, which actually gives us a path to get to data. So we don't have to read the entire table all the time. So the idea is index, the reference point, leads to the data location within the table. So you don't have to read everything. You can find exactly where in the database something is located. All right. And this is Dr. Codd's rules. And this is 50 years old now, so and pretty much accepted. So I don't, not going to see a lot of changes on this. Okay, so that is it for our overview of SQL and databases. We'll be working more with this within the labs as well.